It was launched with a monumental promise: to see the unseen, to gaze upon the first light in the cosmos. Now, 3 years into its mission, the James Webb Space Telescope is delivering on that promise in ways we never anticipated. It has become our guide on an exhilarating journey through space and time, revealing a universe far more surprising and dynamic than our textbooks ever described. Our story begins at the very beginning. We expected the first galaxies to be small, wispy collections of stars. Instead, Webb found them to be shockingly massive and bright, far more structured and developed than our theories allowed. And at their hearts, supermassive black holes were already titans, growing faster and earlier than we ever thought possible. The cosmic rulebook for the early universe is being completely rewritten. Closer to home, in both space and time, Webb is providing a stunning new look at how stars and galaxies grow. It's captured the intricate, dusty tendrils of stellar nurseries, like the iconic pillars of creation, revealing the chaotic birth of stars in unprecedented detail. It's even found crucial new evidence for how galaxies themselves merge and evolve over billions of years. But perhaps the most profound search is for the ingredients of life elsewhere. Webb has made the first ever detection of a key carbon molecule, a fundamental building block for life, in a young planet-forming disk. It has sniffed the atmospheres of distant exoplanets, finding the chemical fingerprints of water, methane, and carbon dioxide. Yet, it also brings deep puzzles. It showed a rocky world, TRAPPIST-1b, that appears to be a bare rock with no atmosphere at all, challenging our ideas of planet formation. On another, it detected a tantalizing hint of water vapor around a rocky planet in its star's habitable zone, though the source remains a mystery. And Webb hasn't ignored our own cosmic backyard. It has delivered breathtaking images of Jupiter's ethereal auroras, Saturn's glowing rings, and the turbulent dynamic storms on distant Uranus. Even the end of a star's life holds new secrets. Webb's look at the well-known supernova remnant, Cassiopeia A, revealed complex, unexpected structures, showing we still have much to learn about even the most studied objects in our sky. From the first light to our planetary neighbors, the James Webb Space Telescope has shown us that the universe is more dynamic, more complex, and more surprising than we ever dared to imagine. Every new image asks more questions than it answers, proving that after just 3 years, this incredible journey of discovery has only just begun. Gaze up into the night sky from the southern hemisphere, and you'll see the third brightest star shining back at you. For millennia, it was just another brilliant point of light, but this brilliance hides a secret. This is Alpha Centauri, our closest stellar neighbor, and it isn't one star, but a fascinating triple star system. At its heart lie two sun-like stars, Alpha Centauri A and Alpha Centauri B. They are a cosmic couple, locked in a gravitational dance that takes nearly 80 years to complete. Their orbit is immense. At their closest, they are separated by the distance from our Sun to Saturn, and at their farthest, they swing out to the distance of Neptune. Alpha Centauri A is a G-type star, a virtual twin of our own Sun, while its companion, B, is a slightly smaller and cooler K-type star, glowing with an orange hue. But neither of these is the closest star to Earth. That title belongs to a faint, overlooked sibling in this system, a small, cool red dwarf named Proxima Centauri. True to its name, which means nearest in Latin, Proxima Centauri is the undisputed closest star to our solar system, sitting just 4.24 light-years away. It orbits its two larger companions from an incredible distance, so far that it takes over 500,000 years to complete a single trip around them. And it's here, orbiting this dim ember, that the story becomes truly profound. In 2016, astronomers confirmed the existence of a planet, Proxima Centauri b. This world is roughly the size of Earth and orbits directly within its star's habitable zone, that tantalizing region where temperatures could be just right for liquid water to pool on its surface. The discovery instantly transformed our neighbor from a point of interest into a prime candidate in the search for life beyond our solar system. Of course, a close neighbor doesn't mean a welcoming one. Proxima Centauri is a volatile star, known to unleash powerful stellar flares that could blast any nearby planet with intense radiation, making the development of life a challenge. Still, the Alpha Centauri system stands as a cosmic landmark. It is the first signpost on the interstellar road, a constant, shining reminder that just across an ocean of space, another star system with another world awaits our discovery. It is the ultimate next-door neighbor, beckoning us to wonder what lies just beyond our own cosmic backyard. Imagine holding two coins, spun together in a special way. You give one to a friend who travels to the other side of the world. The moment you look at your coin and see its heads, you instantly know, without a shadow of a doubt, that your friend's coin is tails. This isn't magic. This is the strange and wonderful reality of quantum entanglement. Albert Einstein famously called it spooky action at a distance. It's a ghostly connection between two particles, where the state of one is intrinsically tied to the other, no matter the distance separating them. This bizarre feature of the quantum world has been proven time and again, earning a Nobel Prize in 2022 and powering the next generation of technology in computing and cryptography. But for all we knew, this phenomenon was a feature of the low-energy microscopic realm. What would happen if we looked for it in the most extreme high-energy environment on Earth? Enter the Large Hadron Collider, the most powerful particle accelerator ever built. Here, deep beneath the Swiss-French border, scientists at the ATLAS and CMS experiments have made a landmark discovery. For the first time, they have witnessed quantum entanglement at the highest energies ever recorded and in a completely new system, the top quark. The top quark is the heavyweight champion of fundamental particles, so massive that it decays almost instantly. This fleeting existence makes it a perfect, pristine laboratory for studying quantum properties before the universe has a chance to interfere. The teams at the LHC sifted through petabytes of data from proton-proton collisions, looking for pairs of top quarks born together in the fiery aftermath. The theory was simple. If these quarks were entangled, their spins, a quantum version of angular momentum, would be linked. Since the quarks decay too fast to see directly, the scientists did something clever. They measured the directions of the particles that the quarks decayed into. The angle between these decay products held the secret, and the secret was revealed, with a statistical certainty that leaves no room for doubt. Both the ATLAS and CMS teams confirmed it. The top quarks were entangled. Their spins were locked in a cosmic dance from the moment of their creation. The CMS collaboration pushed the boundaries even further. They found entanglement even between quarks flying apart at tremendous speeds. The distance and time between their decays were such that no classical signal, not even one traveling at the speed of light, could have passed between them. This was pure, unadulterated quantum spookiness, playing out at an energy scale 1 trillion times higher than your typical tabletop experiment. So why does this matter? Because it opens an entirely new window onto the universe. As CMS spokesperson Patricia McBride puts it, we can now test the standard model of particle physics in new ways. We have a new tool. By measuring entanglement in this high-energy playground, we can search for tiny deviations from our predictions, cracks in our current understanding that could point the way to new particles, new forces, and a deeper theory of everything. This discovery doesn't just confirm what we know about the quantum world. It forges a new link between the very small and the very powerful, and it gives physicists a rich, new menu for exploration. The spooky action Einstein once puzzled over is now a fundamental probe, helping us unlock the deepest secrets of our universe. What if I told you a computer just solved a problem in under 5 minutes that would take the fastest supercomputer on Earth 10 septillion years? That's a 1 with 25 zeros after it, an age far longer than the universe has existed. This isn't science fiction. This is the reality of Google's new quantum computer chip, nicknamed Willow. But this incredible achievement has sparked a debate that goes far beyond processing power. It's forcing scientists to ask a mind-bending question. Did this computer prove the existence of parallel universes? The idea comes from Hartmut Neven, the founder of Google's quantum AI team. He argues that the only way to explain this impossible speed is to embrace one of the most bizarre ideas in physics, the multiverse. This theory, pioneered by physicists like David Deutsch, suggests that every time a quantum event happens, the universe splits. Every possible outcome occurs, each in its own separate, parallel reality. Deutsch proposed that a quantum computer isn't just working in our universe. It's so powerful because it's outsourcing the computational work to countless versions of itself across these other universes, then bringing the answer back to ours. When Neven saw Willow's performance, he claimed it lent credence to this very idea that quantum computing is a direct window into the multiverse at work. But here's where the story splits into two universes of its own. Many physicists are pushing back, hard. Critics, like scientist Ethan Siegel, argue that this is a huge leap. They say you don't need to invoke parallel worlds to explain quantum mechanics. The counter-argument is that the strange phenomena that power quantum computers, like particles existing in multiple states at once, are simply a fundamental mathematical property of our one universe. They claim Neven is mistaking a complex mathematical space for a physical reality teeming with alternate worlds. Furthermore, they point out that the problem Willow solved, called random circuit sampling, is a custom-built benchmark designed to show off a quantum computer's strengths. It doesn't have a practical application yet, and there's no direct, physical evidence of other universes in the data. The link, they say, remains purely philosophical. So what does Willow's achievement really prove? One thing is certain. It marks a monumental leap forward in quantum computing, demonstrating a power that is truly beginning to defy classical imagination. It shows we're getting better at controlling the fragile quantum world, which could one day revolutionize everything from medicine to material science. But has it proven the multiverse? The honest answer is no. For now, it remains a tantalizing, unproven theory. Perhaps the most important takeaway is the debate itself. These incredible new machines are no longer just tools for solving problems. They are becoming instruments that force us to confront the deepest, most fundamental questions about the nature of reality. And in our universe, that's a conversation that is only just beginning. Since the dawn of humanity, we have looked to the stars and asked the biggest questions imaginable. What is the ultimate fate of our universe? Today, we are closer than ever to an answer, but a profound cosmic mystery has deepened. For over a century, we have known the universe is expanding. Galaxies are rushing away from each other like raisins in a rising loaf of bread. But the critical question has always been, how fast? The speed of this expansion holds the key to our cosmic destiny. For decades, the Hubble Space Telescope has been our primary yardstick. Astronomers, led by Nobel laureate Adam Rees, used it to measure the expansion rate by observing special stars called Cepheid variables. These stars act as perfect cosmic mile markers. They pulse at a rate directly tied to their true brightness. By measuring them, scientists calculated a precise speed for our modern universe. But this created a puzzle. The expansion rate measured by Hubble was consistently faster than the rate predicted from studying the early universe, the faint afterglow of the Big Bang. Was this Hubble tension a real feature of the cosmos, or just a measurement error? To solve it, we called in the ultimate arbiter, the James Webb Space Telescope. With its razor-sharp infrared vision, Webb can peer through cosmic dust and isolate these stars with breathtaking clarity. If Hubble's data was flawed, Webb would prove it. The team pointed Webb at the same mile markers Hubble had studied. The result was stunning. Webb found no errors. it confirmed Hubble's data with even greater confidence. The measurements were right all along. As Adam Rees stated, with measurement errors ruled out, what remains is the, quote, real and exciting possibility that we have misunderstood the universe. So what does this mean? It means the Hubble tension is real. Our standard model of cosmology appears to be missing something, perhaps a strange form of early dark energy, or some other new physics that changed cosmic history. This brings us to the final question. What is our ultimate fate? The faster-than-expected expansion points toward a dramatic and lonely end, a scenario known as the Big Freeze or the Big Rip. In this future, the accelerating expansion will never stop. Galaxies will be pulled so far apart they will vanish from each other's sight. Stars will burn out. Eventually, the very fabric of space-time could be stretched so violently that atoms themselves are torn asunder, leaving behind nothing but a cold, dark, and empty void. The puzzle persists, but by confirming it, Webb and Hubble have not failed. They have given us a new, sharper map of our cosmos and pointed us toward the unknown territory where our next great discovery awaits. The discovery that will finally reveal our ultimate cosmic destiny. In the sterile hum of the quantum optics lab, Dr. Eris Thorne holds his breath. Before him, suspended in an intricate web of lasers, is a single electron, but it is not a thing in the way we understand it. It is a ghost of potential, a cloud of probability described by a wave function, existing in a perfect, shimmering superposition of both spin up and spin down. Eris leans forward, his finger hovering over the measurement control. This is the moment of truth. He engages the detectors. For a trillionth of a second, reality hangs in the balance. Then it happens. The wave function collapses. The ghostly cloud snaps into a single, definite reality. On his monitor, a data point appears. Spin up. The experiment is a success. The other possibility has vanished, erased from existence. Or has it? The story doesn't end there. According to one of physics' most elegant theories, the wave function never truly collapsed. It fractured. The universe did not choose a path. It followed all of them. In timeline A, the universe we perceive, Dr. Thorne nods, satisfied. He records the result in his logbook. Trial 734, spin up. He leans back, takes a sip of his now lukewarm coffee, and begins resetting the apparatus. For him, reality continues along a singular, unbroken line. But in that same instant, another reality branched away. In timeline B, an identical Dr. Eris Thorne also leans back from his console. His screen reads, spin down. He too records the result in his identical logbook. He too sips his coffee, completely unaware that he is now a resident of a parallel world, just as real as the first. He is not a ghost or a copy. He simply is. This isn't just a philosophical fancy. It is the many worlds interpretation of quantum mechanics, and hints that support it are beginning to emerge. Look to the cosmos. Astronomers face the Hubble tension, a profound mystery where the universe is expanding faster today than our models, based on its early history predict. Some speculative theories suggest this could be a subtle gravitational tug from a neighboring universe in the grander multiverse. The many worlds theory requires no magical collapse. It simply follows the mathematics of the wave function to its logical, awesome conclusion. And so, Dr. Thorne, now two men, identical in every way save for the memory of a single quantum event, continues his work. Each is a pioneer, charting a course through a separate reality, unaware that they are living proof that reality is not a single line, but an endlessly branching tree, where every quantum choice does not erase a possibility. Have you ever wondered why you can't just walk through a wall? Why matter is solid? The answer lies in one of the most fundamental and powerful rules in the universe, the Pauli exclusion principle. Formulated by the brilliant physicist Wolfgang Pauli, The principle is surprisingly simple. It states that two identical fundamental particles called fermions cannot occupy the same quantum state at the same time. Think of it like assigned seating in a cosmic theater. Every electron, proton, and neutron has its own unique ticket. Inside an atom, this means no two electrons can have the exact same set of quantum numbers, which are like their unique address and spin direction. This forces electrons into different energy levels, or shells, creating the atomic structure that underlies all of chemistry and the periodic table. This is the reason matter takes up space and feels solid. It's the universe's way of saying no trespassing on a subatomic level. And here lies a stunning paradox. Despite this feeling of solidity, an atom is almost entirely empty space. If the nucleus of an atom were the size of a marble placed on the center of a football field, the nearest electrons would be like tiny specks of dust whirling around the outermost seats. The vast expanse in between is empty, so the solidity you feel isn't from matter being tightly packed. It's the powerful no trespassing rule of the Pauli principle, acting across this emptiness, that creates the impenetrable force fields we perceive as a solid surface. But this principle does more than just build our world. It operates on a scale that is almost impossibly grand. When a star much more massive than our sun dies, it collapses under its own colossal gravity. The pressure becomes so immense that it overcomes the forces separating atoms, smashing electrons and protons together to create a superdense ball of neutrons. This is a neutron star, an object with the mass of one or two suns, crushed into a sphere the size of a city. So what stops gravity from crushing it all the way down into a black hole? The Pauli exclusion principle. The neutrons, being fermions, are now subject to this rule. As gravity tries to squeeze them into the same space and energy state, the principle says no. The neutrons are forced into higher and higher energy levels, creating a tremendous outward pressure. This is called neutron degeneracy pressure, and it is the only thing standing against the star's complete gravitational collapse. This quantum pushback is powerful enough to support the entire, unimaginably dense star. The Pauli exclusion principle is a true cosmic architect. A less extreme version, called electron degeneracy pressure, is what supports the remnants of smaller stars, the white dwarfs. So, from the shape of atoms and the diversity of chemical bonds to the very existence of some of the most extreme objects in the cosmos, this one quantum rule is at work. It's a profound reminder that the largest structures in the universe are often governed by the smallest, most fundamental laws of nature. The Pauli exclusion principle doesn't just keep your hand from passing through a wall, it holds up the stars themselves. The world around us feels solid, stable, and real. It's all made of atoms, which are themselves made of protons and neutrons. And inside them we find the fundamental building blocks, up and down quarks. This is normal matter. For all of history, we believed this was the ultimate ground state of the universe, the most stable, most fundamental way matter could exist. But what if it isn't? What if our universe is living in a fragile, metastable state, and there's something far more stable and far more dangerous? Deep inside the cosmic crush of a neutron star, the laws of physics are pushed to their absolute limits. Under pressures we can barely imagine, protons and neutrons dissolve into a dense soup of their constituent quarks. Here, something remarkable can happen. The intense energy can cause some of the up and down quarks to transform into a heavier, more exotic type, the strange quark. This gives rise to a new hypothetical substance, strange matter, a dense liquid made of roughly equal numbers of up, down, and strange quarks. According to the strange matter hypothesis, this three-quark configuration could be the true ground state of matter. It's more stable than the protons and neutrons that make up you, me, and everything we've ever known. The matter of our entire universe might be like a diamond, waiting for the right stimulus to collapse into something denser. If this hypothesis is true, then small, stable fragments of this substance, called strangelets, could exist. They could be forged in the collision of two neutron stars and flung across the cosmos, And this is where the theory becomes terrifying. A strangelet is predicted to have a unique and devastating property. Because it is more stable than normal matter, any atomic nucleus it touches would be converted. Upon contact, the strangelet would begin to absorb the neutrons and protons, rearranging their quarks into the more stable strange configuration. The process would be catalytic, turning normal matter into more strange matter and releasing a burst of energy. This is the Ice-9 scenario, named after the fictional substance in Kurt Vonnegut's novel Cat's Cradle. In the book, a single crystal of Ice-9 could freeze the world's oceans. A single strangelet could, in theory, do something far worse. If a single, stable strangelet were to strike the Earth, it could start a chain reaction. It would consume our planet from the inside out, converting it atom by atom into a hot, dense sphere of strange matter just a few dozen meters across. Everything we are and everything we've ever built would be annihilated in a flash. Now, physicists believe this is an extremely unlikely scenario. Most models suggest that strangelets created in space would be unstable or positively charged, repelling them from atomic nuclei. Experiments on Earth have not produced any stable strange matter, and the fact that the Moon and Earth are still here after being bombarded by cosmic rays for billions of years suggests we are safe. But the hypothesis remains. In the vast, dark corners of the universe, there may be a form of matter so perfect, so stable, that it would instantly and effortlessly erase our own. We believe our universe is real, that the ground beneath our feet is solid, and the stars above are fixed. But what if it's all a grand illusion? What if reality is far stranger, more fragile, and more complex than we can possibly imagine? Some of our most brilliant physical theories, when pushed to their absolute limits, suggest exactly that. These aren't just philosophical musings. They are the startling possibilities that emerge from the mathematics that governs our cosmos. First, the holographic principle. It suggests that your life in 3 dimensions, every sight, sound, and feeling, might be an illusion. This theory, born from the physics of black holes, proposes that our entire 3D universe is a complex projection of information stored on a distant, 2-dimensional surface that surrounds us, like a cosmic hard drive. Everything that has ever happened and ever will happen is just the unfolding of a script written on the edge of the cosmos. Your sense of depth, your freedom of choice, all an elaborate hologram. But what if the illusion is even deeper? The simulation hypothesis argues that our entire universe is a hyper-advanced computer program. The logic is simple. If any civilization ever becomes advanced enough to simulate a universe, then simulated universes will inevitably outnumber the one base reality. Statistically, it becomes almost certain that we are living in one of the simulations. The laws of physics are just lines of code. Your consciousness is part of the program. And the most unsettling part, a simulation can be turned off. Perhaps the most terrifying theory is that our universe exists in a fragile, temporary state. It's called false vacuum decay. Think of it like a drop of water perched on a mountaintop, stable for now, but not in its lowest energy state. At any moment, a random quantum event could nudge a patch of our universe into its true, more stable state. If this happened, a bubble of true vacuum would expand at the speed of light, instantly rewriting the laws of physics and erasing everything it touched. We would never see it coming. In a flash, everything would simply cease to be. But for every end, there is a beginning. Black hole cosmology offers a potential answer to the question, what came before the Big Bang? The math describing the infinitely dense singularity of a black hole is remarkably similar to the math of our own universe's origin. This theory suggests that every time a black hole forms, the matter it crushes doesn't just disappear, it bounces and expands into a new, separate spacetime, a child universe. Our entire cosmos could be the offspring of a black hole from a parent universe, creating an endless, cosmic family tree. Holograms, simulations, fragile realities, and cosmic ancestry. These ideas stretch the limits of our imagination, reminding us that the solid world we know may be just one page in a much grander and much stranger story. From the grandest ocean to the humblest cell, one substance connects all life as we know it: water. It is the universal solvent, the stage on which the chemical dance of life is performed. Its unique ability to dissolve more substances than any other liquid allows it to transport the vital nutrients and minerals that every living organism needs to survive. It builds our proteins, copies our DNA, and moderates our planet's climate. For life on Earth, water isn't just important, it is the matrix of existence. So how did this dance begin? The leading theory takes us back 4 billion years to a primordial soup. In warm, shallow ponds, or perhaps in the fiery, nutrient-rich chasms of deep-sea hydrothermal vents, water was the cradle. It mixed a cocktail of simple chemicals, energized by lightning or geothermal heat. Over millions of years, these chemicals linked together, forming the first complex molecules, the first self-replicating strands of RNA, and eventually, the first simple cells. In the turbulent, life-giving waters of a young Earth, the first spark of biology was ignited. But is our way the only way? We are carbon-based life forms, utterly dependent on liquid water. But the universe is vast and endlessly creative. Scientists now seriously consider the possibility of alternative biochemistry. Could life exist on a world like Titan, where temperatures are so low that water is hard as rock, but liquid methane flows in rivers and lakes? Could this freezing liquid methane take the place of water, supporting a slow, strange form of silicon-based life? The honest answer is, we don't know. The universe isn't required to play by our rules. And yet, in our search for life beyond Earth, we start with what we know. We follow the water. In our own solar system, the clues are tantalizing. Jupiter's moon Europa and Saturn's moon Enceladus are hidden water worlds believed to harbor vast, salty oceans beneath their thick shells of ice. Enceladus even erupts geysers of this water into space, proving a liquid sea exists below. And further afield, the discoveries are staggering. We found water vapor in the atmospheres of giant exoplanets and on super-Earths like K2-18b, a world that could be a Hycean planet, a hot, water-covered world with a hydrogen-rich atmosphere. Each discovery brings us closer to answering the ultimate question. While life might take forms we can't yet imagine, the shimmering, life-giving signature of water remains our brightest beacon in the cosmic dark, our most promising guide in the search for a second Genesis.